Hello friends, welcome to Incredible Physics. This channel provides you a complete solution of each concept of physics, whether you are in class 11th, 12th or preparing for the various types of competitive examinations. It consists summarized theoretical concepts and numericals related to it. If you are new on this channel, please subscribe it and press the bell icon button for the notifications. Now friends, let us start. Now we have to see how can we find the equivalent impedance of an LCR circuit where all the three components are connected in parallel combination. We can solve this problem by two methods. Number one, phasor diagram, and second one by using the complex number. So first of all, we are going to use phasor diagram. In phasor diagram, we have to draw potential and current of the circuit, and we have to draw the common part always along the x-axis, and that is the potential. In this case, current of capacitor leads by pi by 2 radian and current of inductor lags by pi by 2 radian to the potential. Now we can say, and current of resistor is in phase with the potential. Now we can see three currents in the circuit, IL, IC and IR. Because IC and IL are in out of phase, so we can find the result of IC and IL as IC minus IL, assuming that IC is greater than IL. And the second one, current IR, is along the x-axis as well the potential of the circuit. So this is the net current of the circuit, which subtends an angle phi with the potential. The net current can be obtained by under root IC minus IL square plus IR square, and we can write the net current as V by Z, where Z is the impedance of the circuit. In case of IC, we can write it as V over XC minus IL is V over XL square plus this is V over R square. We can see V is going to be eliminated here. So the result is 1 upon Z equals under root 1 over XC minus 1 over XL square plus 1 over R square. So this is the result where we can say Z is the impedance of the circuit. We can find Z from the equation. Now we have to use the second method for finding the impedance of the circuit, and that is by using the complex number. We can write any of the resistance in the form of A plus JB, where J is behaving like iota because we are expressing current in terms of I. That is why we have taken iota in terms of J. This is the imaginary part of the complex number and A is the real part of the imaginary number. We can find the impedance of the LCR circuit in alternating current if we express the resistance of inductor and capacitor in terms of the complex number. Then we have to assume resistance of the resistor as R, while resistance of the inductor as J into XL, where XL is the inductive reactance of the circuit or the inductor. RC equals minus JXC. Now we have to draw the circuit again. In circuit, now we have one RL resistor, one RC resistor, and last one, it is a resistor R. Now we are connecting them in parallel combination. This one is IL, this one is IC, and this one is IR. Now we can treat It is a combination of the resistors only, because all the three resistors are connected in parallel combination. So we can find the equivalent resistance, or we can say the impedance, by using the parallel combination of the resistors. That is 1 over Z equals 1 over R plus 1 over RL plus 1 over RC. After placing the values, it is 1 over Z equal 1 over R plus 1 over JXL minus 1 over JXC, and it can be represented as 1 over R minus J over XL, because J square equals minus 1. That's a property of iota. Similarly, we can write it as J over XC. Now 1 over Z can be written as 1 over R minus J times 1 over XL minus 1 over XC. Now we can see there are two parts. 1 over R is the real part of this complex number, and 1 over XL minus 1 upon XC is the imaginary part of the complex number. Now we can find the mode of 1 over Z, and it can be represented as under root 1 over R square plus 1 over XL minus 1 over XC square. Like this, we have obtained the same result as we obtained in case of the phasor diagram. So we have two methods to solve these type of problems.